morning. I have 2 microphones, so that's a very good start. Can you all hear me?
Yes.
Are you all awake?
Yeah.
Maybe. Okay. So today's topic is the materials genome, and in many ways this is where material science is going to go in the future. And there are some hints in there on what scientific careers might be advantageous to follow because they lead to a job when you're done graduating. And so I'm trying to do that. But before we actually go, remember when you measured the size of the ice sheet and you put the little kind of grid on there and you went home and entered your values? Well, quite a few of you actually did. And this is the result that I kind of downloaded yesterday. Let me see. The observed ones, so the ones that the professionals in quotes have put up, they are shown in red. And then the ones that some of you put into the spreadsheet are shown in blue. And I don't know. We probably could save a lot of money on research by just having you do this every day, because the agreement between the red ones and the blue ones are certainly within the scatter of these values. So you've done a wonderful job. That's the bottom line. And so Danny couldn't be here today. He just wanted me to show you that. Now, as the tradition has it, I'll tell you something about myself. And I like talking about me a lot, and I can hardly read that without my glasses, so let's see if I remember where I was. I put kind of the most important things on here, and you see my car is right up there. So I actually have a PhD in crystallography, which is not the theory, what healing powers, what crystals have. It's actually learning about, it's essentially a part of material science, even though probably if I were in the healing business, I might be able to actually have a bigger salary. Once I've done my PhD, and that's a theme that will come up. Some of the really beautiful thing about science is it's truly international. I did my first postdoc in Australia at the Australian National University in Canberra. Who knows what the capital of Australia is? Okay. Who thinks Sydney? Sure, raise of hand. Any other choices? Actually, Canberra is the capital of Australia, which I didn't know until we actually moved there. The story goes is that when Australia was kind of formed in quotes, there was already Sydney and Melbourne were the 2 largest cities at the time, and everybody said, well, we're going to join this Australian Federation thing provided the others are not the capital. So they sent out an expedition inland to find a site on the green somewhere for the nation's capital. And it wasn't allowed to be at the coast either, because then there was a danger that the city would become more important than Melbourne or Sydney was at the time. So they founded Canberra, which is about an hour's drive inland. And there are early pictures of the new Parliament House where you have cows, green, and the Parliament House, and that was the capital. Now it's a civil servant city, and then the Australian National University is there. After that, we moved to the US. I was at Michigan State University. Lucas, who sits there, who I'm not allowed to mention, was born in Lansing, Michigan. And then I got my job, and you see what I did mostly here. I moved to Los Alamos National Laboratory, where there's a similar neutron source to the spallation neutron source we have here, and I built this instrument that I'm clearly quite proud of as I'm showing it. And I actually was there for 10 years before the opportunity came to come to Oak Ridge, and I'll talk a little bit about why I might have come to Oak Ridge and what are the cool things about the lab here. So I started off as the group leader for diffraction, and very recently I actually became chief for everything data, or more officially the director for neutron data analysis and visualization, which barely fits on a business card, you really kind of. And this is my new division. Now I kind of promised I wouldn't put kids' pictures in there, but I couldn't resist. Okay, so it's a few years ago, but there it is, my daughter and my son. I talked about science being international, and to me this is certainly one of the things, and you probably have spotted my non-Tennessee accent by now. I'm from Germany originally, so that's part of that. This map shows the locations of the institutes of all the collaborators that I've ever co-authored a scientific paper with. And you see, there's a lot of Europe, a lot of North America. We actually have a collaborator down here, Australia, lots of Japan and like Asia there, and then actually there's one department in India that we work with on a regular basis. So, if you do science, you really do kind of a worldwide activity, and to me that's one of the real attractions. Oh, the middle bit was supposed to be a question. It wasn't supposed to come up. Okay. So don't read materials when I ask you, right? Then just give me another answer. So let's think about why science is important. And these are the kind of charts you find in a lot of official documents. What are the biggest threats to society in general moving forward, or the biggest needs we have. A very obvious one is clean energy. You know, we need enough energy for the things we do, but we also need to do it in a way that's sustainable with the environment. Clean energy. The environment in general, right? If we screw up our planet, then there's not going to be a good future. Oops, wrong button. See, I wanted to show them again. Human welfare, you know, health, that's another very important thing. And last not least, you know, national security, and that's in the widest sense. You know, you want to be safe in your country. And my question would have been, what do all these have in common? So what do all these have in common?
They require materials.
Awesome. Well done. That's exactly the point, you know. And one of the, let's see. Let's talk about how we actually find new materials. How does this discovery process work? And how do we end up with an iPod? And there's one version that I'm going to show you. It's probably my favorite one.
I notice you're still working with polymers.
Still? What else would I be working with?
What else indeed? I'll put it another way. How thick would a piece of your plexiglass need to be at 60 feet by 10 feet to withstand the pressure of 18,000 cubic feet of water?
Oh, that's easy. 6 inches. You carry stuff that big and stop.
I have noticed. Now suppose, just suppose, I were to show you a way to manufacture a wall that would do the same job, but be only 1 inch thick. Would that be worth something to you? Eh?
You're joking.
Perhaps the professor could use your computer.
Please.
Computer? Computer? Hello, computer.
Just use the keyboard.
Keyboard. Oh, great.
Transparent aluminum?
That's the ticket, laddie.
Here we go. So what is interesting, okay, first, who knows which movie this was from? Yeah.
It's a Star Trek movie.
Which one?
I don't know which one, but it's like the one with the whales.
The one with the whales. Four.
Was it the last one?
It's, I don't know, but I put a thing in there so I remember. Yeah, so that was from Star Trek for the Voyage Home, and the reason they need this is they need to bring some whales back from the past to save the future, and they need a big tank in their starship, and the kind of plexiglass at the time just, you know, wouldn't hold the amount of water they need to transport the whale. So they have a material science problem. Did you notice how they solved it? What was prominently featured in there, even though it was a rather ancient Mac that they used, and I actually remember working on one of those, you know, it's the whole notion of that we can design a material on a computer with desired properties. And if you look at what this talk is going to be about and where I think some of the future is going, that's exactly that. And I'm not quite sure about the year of the movie, but you know, it's a little bit ago. So we can of course hope that people from the future are coming and they're solving material science problems for us, or we can kind of figure out what we can do ourselves. What is one of the problems? One of the problems is that we have a lot of cool technology, and you know, lots of you have phones and things like that that reflect that technology. But it takes really, really long from a discovery to actually have things on the market that we can use. And this chart shows just some examples on, you know, lithium-ion batteries. You know, kind of, even in the mid-70s, you know, people knew that you could make batteries like that. But it took 20 years until we actually have them in our laptops and on other devices. Pick some other examples you like, you know, thin films. So there's a lot of them. And what all these bars have in common is that they are decades, you know, a decade and a half, 2 decades long. And one of the aims of the Materials Genome project is where we're heading now, is actually to shorten that time. and to use computation and simulation as a large part of it. So those of you who like math and who like computers, there are good times ahead. For all the other ones, we still need experimentalists and people doing experiments, standing in the lab and cooking things, so there are good times ahead for you too. There's good times ahead. So we need to do better. And notice here, even the Nobel Prize then takes even longer, right? So you kind of find something, and then the Nobel Prize actually took, what, probably another 10 years to actually show up. So this really prompted something that is the Materials Genome Initiative. And President Obama, and I need to read this off my screen because I have trouble reading it up there, in 2011 basically announced the Materials Genome Initiative. And the idea there is, you know, to help businesses discover, develop, and deploy new materials twice as fast, we're launching what we call the Materials Genome Initiative. And it talks about iPods and iPads and how this delivery cycle is kind of really long, and that we can do and we need to do it faster. And if you kind of, there's a website, and it's given down here, you know, where there's more details on this initiative if you're kind of interested. And this is one of the flyers. And the two bits I want to kind of focus on is, one is, this is this notion of reducing the development cycle. And one of the reasons it takes so long right now is that we do this in a linear way. You know, we discover a material that has interesting properties. Then we start worrying about if it's toxic to the environment. Then we start worrying about how we put it in a device. Then we start worrying about how to make it cheaper. So it's a sequential process that takes a long time from a discovery. And by basically intertwining all of these, by already worrying about, you know, how you would manufacture something, what the impact on the environment is, how you can make it potentially more cheaply, and have that kind of inform the fundamental science as well, is one of the ways how we can do this. And if you look at what we need for that, and I'll come back to that, you know, we need computational tools. And so that's a theme that's coming back, and that's what our first activity is actually going to do. We need experimental tools. The spallation neutron source that Ian Anderson kind of introduced is a $1.6 billion facility that is a very powerful experimental tool. There are light sources around the country. They are the pieces of equipment that people have in the laboratories. It's all of that science infrastructure. Two of the challenges that, you know, we need to get better at is, how do we collaborate in a modern way? You know, most scientists don't even know what Facebook is. And so there are maybe more better ways rather than, you know, kind of sending emails back and forth. But even more importantly, how do we share our results? We usually write a scientific paper. And that tells you some of the story, but if you ever try to reproduce something from a scientific paper alone, you will discover a lot of the nitty-gritty, a lot of the details you need to know, actually usually not in there. And one of the new directions that is going, that, you know, powerful computers and search algorithms allow us to do, is to think of repositories for those results. Crystallography, which is the science of, you know, kind of figuring out the atomic structure, does that very well. When you solve a structure as a scientist and you want to publish it, there's a very specific formatted file that you need to submit with your results, and it goes in a database. And if I want to go and find out all the cases of bond lengths between an atom A and an atom B of all the structures ever solved, I can go to a database and I can find that out. So I can do data mining. I can benefit from the scientific results that other people had before me. This is not true in all areas of science, and we need to get much better at that. And it's a very difficult project, because for the data to be meaningful, you need to make sure they include all the information that is relevant to it. And everybody does the experiment a little different, so having common standards and doing that might sound easy, but in practice it is not. And so there's a lot of emphasis on that, and we're learning from people that do social media, from companies like Google that figure out what you like to buy. They're into data mining big time. They read all your email and they kind of figure out what you do next, and they send you the right ad on the right of your email at the right moment. There's a lot of science in there. If you think about it, how many email accounts are there? How people track what Facebook people are doing. I mean, how does Facebook make its money? They look at your social data and they do science with it. And they inform companies what products, what other things, right? Otherwise Facebook wouldn't be free. You would pay $100 a month to be on it. And so nobody wants that. So there's a whole area in big data that hasn't permeated into the kind of material science I'm talking about, and there's a big opportunity for that to go ahead. And what's really central to all of this is this notion of that our experimental tools, our computational tools, and the kind of data we have kind of go together. And again, this is clean energy, human welfare. Here's the one for you. Building the next generation workforce. If we have an ad out for somebody in computational material science or somebody who can do some of these things, the pool of qualified applicants is very small. This is something that we, that we need more people of, and we need to train the generation that are coming up to be good at these kind of things. So again, imagine your name in here. So that's kind of one of the other things. It's good times, I said that before, right? If you're interested in science, this is beautiful. An example where this is actually done on a rather small scale, sharing information, is this so-called Materials project, and there's the link up there. And there are some numbers here, but there's actually, for instance, a lithium battery explorer. So you're thinking about making a new battery, and you need to worry about a lot of things. What elements, what's the electrical potential between this and that. And if you click on this and you have an account, you can actually search a lot of information other people put in. You can use things that predict structures, and they actually use high-performance computing in the background to do that. It's a very intuitive, very simple interface. So it has started in small pockets to go down that particular path. And there is Moogle, which is the materials version of Google, as I learned. And so, okay, Genome Project. There is, of course, another one, a predecessor, a famous one, and that's the Human Genome Project. And I just took some data off the internet, so the goal there is, and it was completed in 2003, is to get about the 25 roundabout genes of the human DNA identified, determine about 3 billion base pairs, and then store that information in databases. Remember when I talked big data? So people can look at it. We can correlate diseases and other pieces of information to the human genome, and then improve the tools how we can actually deal with these data. I found this cartoon I couldn't resist, so upstairs it says, God, the human genome code is being unraveled. Damn hackers, now I have to change the password. And if you think about it, materials are the same. If we would understood everything that makes up a material's property, we could sit at a computer and say we want something that is as strong as aluminum and be transparent, and we would go for it. Yes?
I'm curious. I've always thought that the problem with that sort of approach was, not necessarily that we don't know everything involved with the material, but that, the computers we have, even with, giants like Titan, aren't powerful enough to consider all of the physical factors.
So I will reveal now that I'm not a theorist. There are people who will believe that, and I think there's some truth to that. They say, well, we just write down the Schrödinger equation and we can actually solve it. We should know everything. And in principle, that's true. And it's also true that we don't have the computational power to do that today for any real system. And we will never, ever be able, certainly not in my lifetime, to do 10 to the 23 atoms in a real full-size simulation. I mean, you can figure out that you need 10 to the 8 titans to do that, which, we're not going to have. So, in principle, that is true. I think by improving, theory and not going to, the most basic one and doing some approximations, we can do something with the computational power we have today and going to have. So, there was another hand back there somewhere. Yes?
Well, I was going to point out that I watched an article recently that talked about how they were trying to explore computers, and that they were good because they would explore multiple possibilities at once, potentially infinite possibilities. And thus, they actually, if we invent them, which we are working on doing, could do just what you're describing.
So if we have a working quantum computer, you're right too. Then there's actually, and I'm not going to give that talk, there's a whole lot of discussion on how we're reaching the end of the silicon age, how we kind of know that we can't make microprocessors any smaller anymore beyond, the 10-ish nanometers we might be able to do. So the improvement in CPU power we have seen is going to come to an end. A lot of the new computer architectures are just doing it massively parallel, putting 100,000 processor cores to a problem. And there are challenges with that as well. One day somebody is going to make a working computer that is not silicon based, and some of these limits we see today might be gone. And so actually supercomputing is a whole separate interesting talk that I'm not going to give. I'm actually not fully qualified either. So coming back to the beginning, why did I come to Oak Ridge? And one of the things, I was a neutron scientist since ever. So, doing experiments with neutron scattering. I did that back in Munich when I did my PhD. Oak Ridge hosts the two you know, the best reactor-based neutron source and the brightest accelerator-based neutron source, the SNS you've heard of. We are also currently home to the fastest, at least openly known, computer in the world. That might last, you know, like 6 months until somebody else builds a faster computer. But at this point in time, you know, we're holding the record. And for everything I'm talking about, Oak Ridge National Laboratory is kind of a perfect match. And this is something we tell our sponsors, give us more money because we're a perfect match. And we really are. We have computation, we have lots of strengths in material science, in material synthesis, in theory. We have, you know, kind of very state-of-the-art characterization tools. You know, there is only one other spallation neutron source in the country, which is quite a bit weaker. We have other things. We have the Center for Nanophase Material Science. So Oak Ridge National Laboratory is a materials laboratory, and we also have the supercomputing. Interestingly enough, the two largest electricity consumers at Oak Ridge National Laboratory is supercomputing and the SNS. I'm not sure if Ian Anderson mentioned that. Who wants to take a guess on the monthly electricity bill that the SNS has to pay? Yeah. $1 million. Good. So you paid attention. Supercomputing is roughly the same. We have the luxury that we can turn off, the SNS can turn off in summer when the TVA rates are the highest because everybody runs air conditioning at home. The people that run simulations wouldn't really appreciate if they couldn't run any simulation in August. So they don't really have that choice. They run throughout the year. Okay. So before, you know, we smoothly ease into our activity and I give you some more details on a particular example, let's look at material characterization. By the way, you might know who this is. This is Tom Mason, the director of Oak Ridge National Laboratory, and he's charging his electrical car. The lab actually has some electrical charging station that if you own a car like a Nissan Leaf or something like that, you can drive up there, you have a parking space nobody else is allowed to be in, you can plug it in and it will charge while you work. And if it all works, you can go home. Otherwise, you're stranded with an empty battery. And battery technology is one of those things. And here comes this development cycle in. Right? A lot of the work on batteries is done on the fundamental science level. You know, how do these things look on the atomic structure? You know, how does the lithium kind of go in between? But what people actually build are real devices. You know, they kind of take lots of that and wrap it together. And then they discover that those batteries catch fire, or they don't last very long, or they do other things that are undesirable. And something we can, for instance, do is we can put a real battery, so this is a real kind of battery that a company that I forgot developed, and we can charge and discharge it while it's in the neutron beam. And not only that, we can actually look at different areas of the battery and essentially extract atomic structural information from that. So at any point on this battery, as we go through the charging, discharging cycle, so here we see the voltage, and here we see the current as we go through that. And all of these peaks here, and you just have to take my word for it, they essentially relate, remember the diffraction grating you had? And you were putting a laser through it, and you had spots on the wall. And when you were figuring out where the spots are, you could figure out what the spacing of the sieve is you were looking at. This is the same information. By looking where these are, we can figure out the spacing between atoms, and essentially with the same math, essentially. And so this gives us, so the problem here is we have a lot of those as the battery changes state, so actually analyzing this and tying it to computational models is non-trivial, and we're still improving on ways of doing that. So we certainly have a lot of experimental data that we could potentially get more information out of, and that's kind of the direction we are going. Okay, I'm going to switch gears a little bit. By the way, all these cartoons here, I had a former summer student who was very handy with Adobe Illustrator. So she made all of these for me. So what are the elements of science? Well, you can read them, so I'll read them to you. One of them is obviously experiment, and that's why I kind of put it in the middle, right? You know, you have an hypothesis, you did that in your science fair projects, and you know how this works. And then you go and you do an experiment, and you look at the results, and it either proves your hypothesis or disproves it, or it's inconclusive and you need to do more experiments. Kind of the three choices you have. Very often, to understand your experiment, you will need theory, which is essentially equations. Something that tells you, or where you can calculate the behavior of the material you're looking at. And we're going to do that. We're going to have equations that are calculating a theoretical function that we're trying to match experimental data with. That's our first. So equations, experiment. Simulation is really where we can use the theory we have and either calculate the result of an experiment or make a prediction. The experiment doesn't have to come first. Very often in high energy physics, you know, you have like off-the-wall theories that simulate something and saying, if we could actually get to this high energy with an accelerator, we would find this particle, right? Higgs, right, for instance. And then the people work really hard to build an accelerator that can actually go there. And then again, two things can happen, right? They reach the energy that the theory and simulation predicted, and they find the particle, and that's a Nobel Prize. Or they don't, and then they need to make another experiment. Or the theorist changes a number and says, oh, I actually need 3 orders of magnitude more in energy, and that's kind of hard to achieve. So these are the three things. Something that is kind of coming into it is this data thing that are colored differently. And that's again the idea that this is basically, a lot of science is done in small teams. So, you know, I have my theorist who has a theory and we simulate something. But if I wanted to learn something about simulation that somebody else did, or I wanted to go through a lot of possibilities without recalculating or remeasuring it, you know, there are only a few examples where you can actually do this readily. Structural databases are an example. And so there's a lot of effort going on, and actually the federal government is giving out money. So that, you know, this is a good area to work in for that reason as well. So we can actually have an infrastructure that if you sit on your desk and you wonder, do all the materials that have lithium and that kind of coordination show the same behavior, that you have a way of finding out if anybody has done this, if there is a common theme, so a whole series of materials. And you know, lots of people, including myself, are sure that if we do this better, we might discover things we wouldn't discover as an individual team ever. So there's like information hidden there. You might collect a whole data set and you're looking for a particular feature because your theory tells you there's a funny structural distortion in your material and this is the area where you should see a peak. So you look at that area and you find the peak and you write your paper. And then your data go on disk and you say, okay, fine, I'll do the next thing. And that's perfectly fine. But there might be something in your data in an area where you didn't look. Because the problem is we now collect data that are not just a curve that you take on a piece of paper and you see everything. We collect data that are gigabytes and terabytes in size that you can't even visualize as a whole. So we need computers to help us to look through that and show us things of interest. And so it is very possible that we have quite a few data lying around on the modern machines we collect them with, where there's an interesting scientific discovery just in there waiting to be found. And again, computers can help us do that. Okay, before I get like looked at angrily because I run too slow, let's get a little bit to some background of the activity. So something we're going to do is you're going to have, well, I should step back. I should tell you about the kind of data and the kind of science we're doing. One of the very powerful applications of diffraction, and again, just think of the little grating example you did with your laser, is that we can actually figure out the positions of atoms in materials, in very complicated materials with the tools we have nowadays. One way of looking at materials is by basically producing something that is called a pair distribution function, which is something I've worked on for 15 years or so, and so I couldn't help it. That's the example we're going to have. In this case, we use nickel powder, so it's a very straightforward model. And what it tells you is basically it maps out how far atoms apart. So a crystal is kind of irregular. Think of a brick wall. So there are atoms in regular distances, right? And we can map out all these atom-atom distances. So what you can immediately tell by looking at this with having a peak at about 2.5, and these units are angstroms, and this is just something we like doing and I couldn't help it. It's not even an allowed unit, it should be nanometers. It's 10 to the minus 10 meters, so it's small. Who knows how many nanometers that is?
How many nanometers are in an angstrom?
Yep.
Well, the nanometer is 10 to the minus 12, no, minus 9.
Yep.
So there would be 10 nanometers, or 10 angstroms in a nanometer.
Very good. And for some reason, people that work in this field, just like Engström. Maybe we like the little A with a circle over it because it's hard to find on the computer keyboard. Anyway, this is my unit. I'm sorry I didn't change it, so I hope I don't confuse anybody. What you see immediately is that the atoms closest together in nickel are 2.5 angstroms apart. The second nearest distance is wherever this is, 3.5 something. And then it kind of goes on because a crystal has a periodicity, so you always know that there's an atom 1 lattice parameter over, 2 lattice parameters over, 3 lattice parameters over. And the lattice parameter we'll see in a minute is just to measure how big that building block is. Okay, so it's a map of atom-atom distances. These were collected on the NPDF instrument that you saw early on that I kind of built. And so what you do is when you have the data which are shown as black circles here, the question is, well, what do you do with it? You can do what I just did. You can say, oh, okay, the nearest neighbor is at 2.5 angstroms and the second nearest neighbor is at 3.5 angstroms. And actually quite often we do that. We might change the temperature and just map out how the width changes and draw some kind of conclusions out of that. So we're not really using a model that we fit against it. But very often you actually want a structural model. Think of that as a list of atom coordinates in the computer, something that you can plot and it looks kind of cool. And we want to adjust parameters in that model to match our observation. And that's kind of what we're going to do manually as part of the activity. So the red line here is a calculated pair distribution function from a model that basically says this is where the nickel atoms are. And you see that there's a pretty good agreement, and quite often we actually put a difference curve underneath so you kind of see what is left where the data are slightly different from the model. And some of this might just be your experimental kind of things that your model doesn't do. So this is what we're going to do. So how do we match the red line? How do we get to do that? We need equations, I promised you that, so there they are. I put some up there. I kind of found really long ones, and I just... Okay, you don't need to understand those. I just, so this goes back to the beginning. We need a model. Okay, we know it's nickel. So this is the lattice parameter, the distance between two atoms. There's actually a shorter distance in here, because in nickel, think of a cube, but in the middle of each face is another atom. So the distance between this atom and that atom is actually shorter than the lattice parameter. And that will become something you're going to see. And then we need a way, when we have this kind of set of coordinates, how do we calculate our experimental quantity, the PDF? And these equations tell you that. And I'm not going to explain them to you, unless you want me to. So this is the theory you need. This is a mechanism by which you can relate your model to the experimental observation you have. And we have a program that does that for us, and we're going to use that. So there are different ways, and I need to make some words kind of clear. So the model we're using is going to have 3 things you can adjust. One is called the scale factor, and if you think back here, this is just, you can basically just scale up and down the theoretical function. So the scale factor will relate to the height of the peaks, as you see that. We have a lattice parameter, and as I mentioned, this is the distance between these two atoms. So it will define where these peaks are. Now there's a trap in there. Because we have a distance that is shorter than the lattice parameter, which is the one going across the face, you actually need to look at this peak to determine the lattice parameter in your activity. It's the second one on your plot, not the first one. And the third one we have, and this has a really long name, it's called the atomic displacement parameter. And these are the words we actually use. We sit in the office and we talk about atomic displacement parameters and things. And they basically give you a measure of how much do the atoms rattle around. And if they rattle around more, then these peaks get broader, because you get a larger distribution of atom-atom distances as they do this. So these are the 3 things we're trying to determine: scale, lattice parameter, atomic displacement parameter. I found another equation. This is kind of telling you there's something called the R value that you're going to see on the handouts, and it's just a measure of how well does your model agree with your data. And if you strip off all the kind of funny looking things here, it's really just the sum of the differences squared between your observation and your calculation. So if you have calculated, if you have something that is in perfect agreement with your observation, all these differences will be 0, and your R value is 0. So a small number is a good agreement, and a large number is a not so good or bad agreement. Don't worry about what the number actually means.
So is that just a residual equation then?
Yeah.
Okay.
And it's normalized in a particular way that we like. But, you know, again, I took it off the manual, off the scientific code that we're going to use. I didn't simplify it, so it's kind of, but you're exactly right, it's a residual equation. Maybe that's some advice I can give you. Never be scared of equations. Even if they fill 5 pages, once you start breaking them down into bits you recognize, they're not scary. Actually, as a physicist, I think what I learned first is never to be scared of an equation. I always go in with the assumption that I understand it. I discover later on that I don't. But just because it's big doesn't mean it's complicated. They're actually very small equations that are very complicated. Okay. So something that is done in a least squares algorithm, that we basically can change these parameters in one of those models to iteratively kind of get the best agreement with our data. And there are 2 things important for that. One is you need to have some starting values. You need to have some guess on what are reasonable values for the scale factor, the lattice parameter, the atomic displacement parameter in our case. You can't just put them all to 0 and hope the program finds it. So you need to do something that kind of looks roughly like what you observe, and then you can have it do the final tweaking, if you will. And you're going to have that. So that's the sensible values. And if you're actually interested how least squares works, you know, on all these things, I have put links on there where you find more information. So this is going to be the handout you're going to see. And actually, this is one of the handouts. So the activity is going to be done in teams. And for the 3 parameters that we want to refine, there are 3 sheets like that. I just picked the example of the lattice parameter. There are going to be 2 other ones that relate to the scale factor and relate to the atomic displacement parameter. They have the same layout, except the numbers and the way the blue and the red function look is different. And so everybody's going to try to estimate one of those parameters as well as they can. Then there's a table where you put all the numbers in it. And then there is a website that is listed on the handout where you enter those values. Now, before I explain this to you in some detail, I want to give you some motivation why we want to do this. When you have entered all your information, we're going to come back here and we're going to take all the numbers that all of you put together and run them through the program and calculate how well it agrees with the experimental data. And it will give us an R value that will tell us how good your agreement is. And I have some prizes on the table for the team that kind of gets the best agreement. So work hard, that's always good. Okay, so just a little bit of, so you're not too confused when you see those. Again, the black data here, or the black circles here, is the experimental data. They're going to be the same on all 3 sheets. That's the experiment we did. And it's the same thing. It tells you the nearest neighbor peak is here and the second one is here. And I just showed a subset of that. The function actually goes on. The 2 lines you see here is the calculation of a model for a nickel structure for 2 different sets, in this case of the lattice parameter. And you see in the blue one, the peak is too far to the left or to short distances, and the red one is just a little bit too far to the right, so it's slightly too large. The 2 values that corresponds to 2 models, you know, model 1 lat plus is this one here, is 3.55, and this is the agreement. So the red one is 3.55, and then the blue one is at 3.45, the shorter one. You can clearly see, you don't need the R value for that, that the blue one fits worse than the red one. It's sometimes remarkable how well the human brain and the eye works. You just see that, you know. So here we go. So when you're trying to make the estimate, you can kind of basically, you could take a ruler or something and figure out what the difference between these 2 is, relate that to the difference between these 2 values. You can estimate where this should go. At the end, you should find a number that's between the 2. So it clearly needs to be larger than 3.45 and slightly smaller than 3.55. And then you add that value in here and you put your name on it. And then on the 4th sheet, you know, one of you is going to record the numbers from all 3 sheets, go to the computer, enter them, and then we're going to run through them here and see what happens. So, be the least squares. So you're basically my refinement program at this point. It's iterative. So if we did this for real, we would take the next set, we would send you back out, do it again until we get as close as we can and keep zooming in so we kind of see these things. We're looking for the best refinement team for 2013. Something you need to remember, when you go out to the tables, they're going to be team numbers. I will not know who you are. When we do this, all I will know is the team number. If you forget which team number you are, then you will not be able to cheer when your plot comes up. So, with that, I'm perfectly on time. Let's go have the activity.
Oh, you can just working really precise. Take a look over to the high power.
Okay, so 36 official responses, if Google is right. Let me reload it one more time to make sure we're not missing anybody. Okay, so before we actually go and run it, there's another piece that's kind of interesting, and this is essentially showing how difficult, how easy you all thought the parameters were to determine. And you know, actually the scale factor and the lattice parameter in terms of easy kind of break even. Nobody really, well, quite a few people thought that the atomic displacement parameter was easy. And maybe that's not surprising because actually most people felt that it is the most complicated one. The scale factor is kind of the one that people found most easy. And there are probably two reasons for that. One is, how sensitive is your model function to the change of the parameter? Right, if you just needed to tweak it by a little bit, the width, it wasn't quite clear where you need to measure it, halfway up, or so this is a tricky one. And even in a least squares refinement program, where these things are driven by partial derivatives, okay, who knows what a partial derivative is? Who knows what a derivative is? Okay, it's nearly the same. It tells you how the function changes as you change one of the parameters. And that's essentially what you did by hand. You had two versions of the function at slightly different parameters, and by looking at that change, you were trying to figure out what the real value is. That in fact is what the program really does. And you will find that if you look at error bars or other things that relate to how much does it vary and how precise you can determine it, you will actually find something that is pretty similar to what your intuitive feeling told you. Which ones are hard, which ones are easy. So what I'm going to do now, I need just a second to download these onto my laptop, and then we're going to run them. And so these are all your numbers. And so what I'm going to do, if I'm really good, so I'm going to save them onto my computer. And then we make this one go away. It hates me. Go away. What have I done? Okay, I just want you to not be here. Here we go. Okay. You might have noticed a slightly arcane font. This is some program that I wrote when I was younger, and so this is why it has an arcane font. What this is going to do is it's going to take every set of numbers that you entered into that table. It will calculate the function and will display it on top of the experimental data you saw, and it will tell us what the R value is. Now I need one volunteer who can be up here and shout out the team names as they come up. So who wants to be here? Okay, here we go. And when the team number, I need the members of the team to go ooh, ah, or something you want to do so we kind of can hear you and we know where you are. So as they're coming up, it will say on the top, team, and then you just read the number behind it and you make them cheer. Okay? Okay, I see. It's getting the data. Okay, unfortunately it looks, there must have been two empty lines in there that kind of don't work. So it looks like none of the teams put something up that was wrong in terms of the range of numbers. So here's the first one.
Team 2.
Ooh, no, there you go. Okay. What it will do, it will keep track on who is the best fit. Of course, this is the first one we look at, and they are the leaders right now. And so as we go to the next one, if somebody goes below 13.43 as an R value, it will be the new best fit. Otherwise, it will display here which team is the one that's currently in the lead. Okay, we need to go through this reasonably quickly. So good job. I like this a lot.
Team 180. What?
Yeah. Okay. Very good. Good agreement. Maybe a little off on the displacement parameter. Not quite as good, but excellent.
Team 7.
That's so funny. Yeah.
Yay! Very nice agreement. Actually, quite close. Team 2 still being in the lead.
Team 28.
A little off on the lattice parameter, but good. Better than it was.
Team 14.
Scale factor a bit too high, but otherwise good.
Team 10.
Second best, but not quite.
Team 8.
Very good.
Team 128.
Where did you get those numbers from?
Team 53.
Okay, they're up there, I can tell. A little too wide, but...
Team 31.
Okay, we have a new leader. 9%. Awesome.
Team 50.
We have another one who's even better. 7.49.
Team 37.
Very good.
Team 38.
We have another one getting even closer at 5.88. So Team 38 being in the lead.
Team 19.
The width is hard to do, so this is a bit off.
Team 5.
Ooh.
Team 29.
Here we go.
Team 12.
I don't hear any cheers. I don't know we can go on.
Team 17.
This is something you get when you make it too narrow. It makes these very interesting ripples, so it looks dramatic, but the values are still kind of close. So some of them are very sensitive, some of them are not.
4.
Where? Is it a single person team?
Team 23.
Very good, also below 10%. We have a new leader, Team 16. Okay.
Team 13.
Actually, nice agreement as well, but you know, we have some very tough competition here.
Team 39.
I think what happened here, you forgot a 0 when you entered it. So you actually made it 10 times as big, so whoever entered it might not have done 0.005, but 0.05. So you actually did, it's probably a typing mistake. So very good. Here we go.
26.
Awesome.
Team 41.
Oh, very good too.
Team 11. Team 24.
4.83, unbelievable.
Team 25.
Okay.
Team 1.
Oh, Team 1 is gone.
Team 32. Team 30. Team 6. Team 3. Team 35.
This might be another that we forgot a 0, so it's kind of flattish looking.
Refinement results.
Okay, so first, thank you so very much for being up here. Hand of applause for our cheerleader. Where's Team 24? Why don't you come down here? I need to see you. I need to look you in the eye. Because what you did a better job than my refinement program did. We could only get to 6.15. So you have to do all my calculations from now onwards because you're better than my computer. So hand of applause for Team 24. Just tell me quickly what t-shirt size you need. Adult large. There's one for you. There is one for you. Large too. Here we go. And another hand for our winning team. I was sitting there yesterday and I thought, is somebody going to beat my refinement? And I worked hard on the refinement. I tried to converge it. It's actually telling you something, that these programs that do these iterative processes on these multi-parameter functions, they not always find the best agreement. It actually takes quite some skill to know how to do that. And so I didn't think anybody would actually be better, but boy was I wrong. They're not only better by a little bit, it's a 6% R factor down to a 4.8. So, yeah, if you need a job when you're done with college, look me up. Okay, so, is there any team who didn't see their results flashing by? Because it's always possible that my script made a mistake. Okay, we're all good? Awesome. So with that, we're going to go. Okay, remember your team number, we did that. And the second part, as we're kind of running late, is really looking at materials that are exciting and some of the other characterization techniques. So thanks to the generosity of ORAU and Oak Ridge National Laboratory, we actually managed to buy, or they managed I should say, to buy little packets that have a few activities in them, and every single one of you can take one home. Out of the 4 activities you can do with it, we're going to limit ourselves to 2, but there's a little booklet, so when you're home, you can actually do some other ones. There's some very cool things we're not going to do today, like an optical fiber. And so you can, you know, shine your light on one end and it comes out the other end. There we go. And, okay, I need to say this in terms of safety. Remember when we kind of did when you took a laser pointer through the grating and it made a diffraction pattern? This is a slide that can do this. But you can do it with an LED flashlight like this. The way you do that is you shine it in your eye and you look at it. Now when you do this experiment with the laser pointer, what you're not going to do. Thank you. You can, if you have a laser pointer at home, you can try these slides with a laser pointer. They should work as well. But please, shine it to the wall and do not shine it in your eye. I don't want to see people with eye patches next week, you know, kind of coming in, because that will not be good. The 2 activities we're going to do, one is a very nifty thing which is called a shaped memory metal, or shaped memory alloy. And essentially what it is, to give you a very brief scientific reason, is there's a phase transition between, so basically there are 2 different structures that it can change from one to the other one. One is stiff and one is bendable. So what you can do with this is you can curl it up, and if you warm it up it goes straight again, and you can do that. There's still active research on shaped memory metals. Some of them you trigger by temperature, some of them you trigger by magnetic field. So you're holding a very cool piece of technology. There are some stems you can actually get in your body. So they go inside, you know, a blood vessel or something, and then by the temperature of the body, they start expanding, so they keep, you know, they keep the flow of blood going. So these are really, really cool ones. You can take one home. The other thing is essentially a fridge magnet. Looks like this. And there's a little thing attached that you take off, which is your probe strip. And what you're supposed to do is with this find out how the little magnets in here are arranged by just sliding this one, and I'm not going to do it, so then you see what happens, by just sliding this little test tip, you know, across the surfaces in the 2 different directions. So in order to give you enough time to play with all of this, I'm going to be done talking now, with one exception. There's one more slide to come. If you really need to leave at 11 because you have another commitment, you can grab one of the nano kits on one of the tables up front in the lobby, so you can do this at home. If you have time, please stay with us and we can play. Essentially, not quite as long as you like, but you know, for a while. The last thing that I brought with me is, if you really want some more in-depth information on some of those things, you know, the Oak Ridge National Laboratory puts these reviews out that are, you know, scientific information for the general public. There are 3 that relate very closely, essentially, to what I talked about. One is Titan Rising, it's about a supercomputer. One is on nanoscience, and this, you know, and one is on Innovation Nation. I'm not sure we have one of each for everybody, but pretty close. They will be out there on tables, and feel free to take one of each, as long as we have some, and take them home and read them and study them, and then we'll have a test next week. No, okay, we don't. With that, go out, have fun, and I'll see you out there.
Thank you. atomic arrangement.